Welcome to Calculus. Today we will investigate finding limits using L'Hopital's rule, taking a look at some of the 5 indeterminate forms. Our first example is the limit as x approaches infinity of 3x times e to the power of negative x. And I see in my instructions that I want to identify what type of indeterminate expression I've got. So the 5 that we're considering would be 0 times infinity, infinity minus infinity, 0 to the power of 0, 1 to the power of infinity, or infinity to the power of 0. So we want to see which one we've got first, and then we need to decide how to proceed from there. So the way we do so is just by direct substitution. So I've got x tending towards infinity. So this is going to be 3 times infinity, which is a form of infinity, times e to the power of negative infinity. So again, e to the power of negative infinity, we can substitute with 0, because basically anything to a negative power is that value in the denominator under 1. So this is the form 0 times infinity, or infinity times 0. And the case is, if we have that indeterminate form, in order for this to be eligible for L'Hopital's rule, I need to get it into one of the other 2 major forms, one of which is 0 divided by 0, or infinity divided by infinity. Those are the forms that I can use L'Hopital's rule to finalize a limit. So I have to kind of take a look here. And I want to use one of the things that we kind of observed when we were doing direct substitution. E to the power of negative x is the same as 1 over e to the power of positive x. So I can rewrite this limit as the limit as x approaches infinity of 3x times 1 over e to the x, or simply over e to the power of x. And if I then apply direct substitution again, what I have is then 3 times infinity, which is a version of infinity, over e to the power of infinity, which is also infinity. And that's now one of my 2 major eligible L'Hopital's rule forms. So I'm going to apply L'Hopital's rule by taking derivative of the numerator and the denominator separately. So over that equals sign, I am going to announce that I am using L'Hopital's rule for the next expression here. And then let's apply it. So that's going to be the limit as x approaches infinity. And then I want to take the derivative of the numerator. So that's derivative of 3x, which is 3, over derivative of the denominator, e to the power of x. Its derivative is itself, e to the power of x. And at that point, again, I can try direct substitution. This is now going to be 3 divided by e to the power of infinity, which is essentially 3 over infinity. And as that denominator becomes larger and larger and larger, this value is going to become 0. And that concludes that limit. So again, just to recap, I want to figure out which of the 5 indeterminate forms I have, and then transform it into one of the 2 indeterminate forms before applying L'Hopital's rule. Let's take a look at our second example. Here I've got the limit as x approaches 0 of 1 over x minus 1 over e to the power of x minus 1. So I want to investigate, first of all, to see which of these 5 I've got. My feeling is this is the difference, infinity minus infinity. And if I do direct substitution, 1 over 0 is basically a way of writing infinity, minus 1 over e to the power of infinity minus 1. And minus 1 won't do a whole lot to this term, e to the power of infinity. That's infinity itself. And so basically I've got 1 divided by infinity, and that's essentially, oh, I see here, I need to flip out this. It's not as x approaches infinity, it's as x approaches 0. And so that'll help us again. So this is again, 1 over e to the power of 0 is 1, 1 minus 1 is 0. So this whole fraction has the value of 1 over 0. And so that confirms that we are looking at the indeterminate form infinity minus infinity. So I've identified that form. I need to transform this now into one of the other two, either 0 divided by 0 or infinity divided by infinity. Again, those are the two forms that are eligible for use of L'Hopital's rule. So just looking at those two forms, they're just single numerator over single denominator. I need to combine my fractions. So I'm going to do some work here to do that combination. So this equals the limit as x approaches 0. And I want to get my denominators the same. So this is going to be 1 over x minus 1 over e to the power of x minus 1. So I want to swap denominators. I'll multiply the first fraction by e to the power of x minus 1 above and below. I'll do the same on the second fraction with the x. And that allows me to combine my two fractions as one. This is now the limit as x approaches 0. My common denominator is going to be x times parentheses e to the power of x minus 1. And my numerator is going to be 1 times e to the power of x minus 1. So e to the power of x minus 1 minus 1 times x, which is just x. So again, I want to try, I've got everything in one fraction. I want to try direct substitution, see if I've got one of my green indeterminate forms. So this, if I plug in 0, is going to be e to the power of 0, which is 1, minus 1, minus 0. So the total value of that numerator is 0. 1 minus 1 minus 0. And then in denominator, 0 plugged in for x times e to the power of 0, which again is 1 minus 1. 0 times 0 is 0. And that is an indeterminate form. I can apply L'Hopital's rule. So let's do that. As I record this now, again, I always announce I'm going to use L'Hopital's rule by writing it over the equal sign as it's occurring. So L'Hopital's rule, and so this is equivalent to the limit as x approaches 0. So I want to take derivative of this numerator, e to the x minus 1 minus x. So derivative of e to the x is itself. Derivative of minus 1 is 0. And derivative of negative x is minus 1. That's all over the derivative of this product, x times e to the x minus 1. And what I'll do is I'm going to distribute that x through to the two terms. So I'm really going to take derivative of x times e to the x minus 1x. So I've got to apply product rule to that first x e to the x. So it's the original x times derivative of e to the x, which is e to the x, plus e to the x times the derivative of x, which is 1. And then minus the derivative of the second x, which again is 1. So to just clean that up so we can check our limit now, that's the limit as x approaches 0. Numerator is just e to the x minus 1. Denominator is x times e to the x plus e to the x minus 1. So again, we should try direct substitution, see if we have something that we can actually take limit now. So again, I'll plug in 0 above, so that's e to the power of 0 minus 1. 1, and that's equivalent to 1 minus 1, or 0. And then in denominator, I've got 0 times e to the power of 0, so that's 0 times anything is just 0, plus e to the power of 0, which is 1, minus 1. So still I've got an indeterminate form, 0 over 0. But remember, I can keep applying L'Hopital's rule. So I'm going to write again here that I'm going to apply the rule. So again, I'll put that this is equivalent to the limit as x approaches 0 of now the derivative of this one in green. So it's derivative of e to the x is e to the x, and then derivative of minus 1 is 0. Now I want to take derivative of my denominator, so that's x times e to the x. So I got to use product rule, plus e to the x times 1. So that's derivative of that first term. Derivative of e to the x is e to the x. And then derivative of minus 1 is 0. So now I got to combine my like terms, let stuff disappear. Let the zeros disappear. So numerator is just e to the x. Denominator, I've got these terms. These are like terms, e to the x plus e to the x. So it's x e to the x plus 2 e to the x. So what I could cancel out here are these e to the x's. And so this just is going to reduce to the limit as x approaches 0 of 1 over x plus 2. And if I apply direct substitution, that's 1 over 0 plus 2, which is 1/2, and that is complete. So we did have to apply L'Hopital's rule twice to that example, but it got us to the limit after both applications were done. Let's take a look at our final example. So here I have the limit as x approaches 0 from the right-hand side of the function x to the power of x. So I can see right away that is the form 0 to the power of 0. And we can think really about how we treated this function x to the power of x when we were trying to take its derivative. We didn't have a whole lot of luck doing that until we thought about using the natural logarithm. And that's really, again, the approach we're going to use here as we try to take the limit as this function x to the power of x approaches 0. So to do this, if you've got this form 0 to the power of 0, there's a sequence of steps that we want to take that use natural logarithm. So I just want to call my function here y equals x to the power of x. And I want to take the natural logarithm of both sides. So I'm going to apply natural log to y. And what that'll do on the right side is it'll take this power and bring it out front using our logarithm rule. So it becomes x times the natural logarithm of the base x. So at that point, what I want to do is I want to say that I'm going to take the limit as x approaches 0 from the right side of the natural logarithm of y. So I'm not going to deal with the function as it is originally. I'm going to deal with it separated. I can say that this is equivalent to the natural, or the limit as x approaches 0 from the right of that right side, x times natural log of x. Now I gotta think for a moment how I'm going to take derivative of that form. So that one, I really need to just check with direct substitution, see what it's going to come out if I plug in 0. So that's going to be 0 times the natural logarithm of 0. And if I think about what that's value is, that's a vertical asymptote on that function. So that is 0 times infinity. So I see that within this process, I'm kind of running against another one of the forms. So what we've got to do is kind of sidestep and evaluate this limit. And then we come back and evaluate the limit that we were tasked with at first. So what I want to do is I want to rewrite this limit of x times natural log of x. And I'm going to call that the limit as x approaches 0 from the right of the natural log of x. I'm leaving this term in the numerator, but I'm going to divide by 1 over x. And essentially, I've just dropped this multiplier x down into the denominator. And when I think about that form, that now is, if I do direct substitution there, that's going to be natural log of 0, which is infinity, as we saw, over 1 divided by 0, which is also infinity. So that's now eligible for us to use L'Hopital's rule. So let's do so. So I'll write equals, and then I'll write L'Hopital's. Again, that just announces, hey, we're using this rule because we've found that it meets the criteria. It's one of the 2 indeterminate forms. So I'm going to take derivative of numerator and denominator. So we'll say this is equivalent to the limit as x approaches 0 from the right. So derivative of natural log of x is 1 over x. Derivative of 1 over x, I'm going to treat this as x to the power of -1. So that's -1 times x to the power of -2. And I can rewrite this to help simplify that complex fraction. That's the limit as x approaches 0 from the right of 1 over x over -1 over x squared. So then I want to combine everything here. I'm going to cancel this denominator by multiplying by -x squared. That'll all become 1. I'll also multiply numerator times -x squared. So that'll give me the limit as x approaches 0 from the right of basically -x. And as I do direct substitution, that has the value of -0, which is just 0. So just to kind of pull things together, what we've established is that if I pull from kind of where I was looking, that this limit has the value of 0. And again, what that's equivalent to is the limit of the natural log of y. So here's where we have to kind of think in terms of how we can shuttle back to the original x to the power of x. And this is what we should write. Since this limit as x approaches 0 from the right of the natural log of y equals 0, which is again what we just established here, then here's our conclusion. The limit as x approaches 0 from the right of just y is going to be equivalent to e to the power of that limit, and the limit we found was 0, so I'll plug that in. And that I can actually evaluate. That equals 1. And that completes our limit here. Again, what we're kind of leaving in the background is that y is x to the power of x. We'd established that at the very beginning. And really all this hinges on this conversion from natural log of y to raising e to the power of this limit there. Well, thank you for joining for this investigation of finding limits using L'Hopital's rule. See you soon.